Alright, so let's start off with, what is a graph? A data structure, it's a data structure that shows the relationship of data. So as you can see, it consists of a bunch of nodes, and these can hold some sort of data, like a number, an age, just anything, just an object. And then we can show relationships between between this data with lines, as you can see here. And these are called edges. So each node is also known as a vertice, as you guys maybe have learned in math class, geometry. And we can basically show relationships between data. And this helps us model complex real-world problems. So examples could be a network of roads. A lot of databases now actually are modeled in this way. And also we can also, for example, show relationships of people. For example, in Facebook, you could show the relationships of like this person is friends with these people, and then this person's friends with these people. That kind of example. So let's get into like the types of some of the properties that edges can have. So as I mentioned before, what was it again? You can show like friends lists and stuff. So as you can see, we have directed edges. So before we just had normal edges, just like normal lines that show, oh, these two nodes are partners. But a directed edge shows some sort of parent and child relationship. So, for example, in this A and B, we have A has a friend B, and B has a friend C. But B does not necessarily have A as its friend. So, as you can see, this is what a directed graph would be. And also, something this could show is the direction of electrical circuits as well. That's an example. And then also, we can have weights for each of these edges, for these relationships between these pieces of data. So these are called weighted graphs, and edges can have some sort of value with them. So for example, going from point 0 to 1, we have a distance of 3, a walking distance. And directed graphs and weighted graphs, you could have a directed weighted graph. It's just a combination. It's just like an edge can have a direction or not have a direction. It's just a property. All right, and then let's get into some node terminology. So as you saw before, so nodes. So if two nodes just have a simple connection between them, they're called neighbors. Two nodes are neighbors if there's like an edge between them. And then they're only a parent and child if the edge is directed. So the parent is the node. So like the parent, for example, it's going to be C, and the child is E, because C is the parent that points towards E, the child. So yeah, that's where we're at. And then let's get into some graph properties as well. So a graph is cyclic or acyclic. So in a graph, a path between two nodes is cyclic if the first node and the last node are the same. So it cycles back to the first one. And then the nodes connect in a path that cycle back to the start. And then another property you can have is connectivity. A graph is connected if there's a pathway between any two nodes. And then we can also have components. The connected parts of a graph are its components. And then here's some pictures just to show you. So cyclic versus acyclic. This is cyclic because we can go from this starting point and go and continue this path and go right back to the starting point. While this is acyclic, we can't really, there's no branch between this first node and this last node. Alright, and this is connectivity, okay? So we can see this entire graph is connected. Every node, there's some sort of pathway you can travel from any node to another node. While this is disconnected, they have three components that are all separately connected, and then this has three components. One component, two component, three components. Connected graph, as you can see, only has one component. Alright, and then with graphs, we can also talk about trees. So trees are a special type of graph. So it's a type of connected graph that has a unique pattern, unique path between any two nodes. So traveling from one node to another, you can have a path, and it's always unique. So a tree is a graph, but a graph is not necessarily a tree. And then a tree commonly contains some sort of root node, so a starting point, so like this 2, for example, and then it starts to branch out and have children. That's why it's called a tree. So as you can see, there's 2 branches out to a 7 and a 5. 7 branches out to 7, to a 6, a 10, and a 2, as you continue. And then it consists of parent nodes. So these are like parent nodes, and then you have your children nodes, and then these children nodes can have their child nodes. If you guys were here for last week's lesson, we did recursion and dynamic programming. This is where you could get into some recursion. As you can see, two will have some children, and then their children has children, and children have their children. So that's an example of a recursion. And a great example would just be like a family tree. A family tree is like your grandpa has his children, and then yeah, it just trickles down. All right, and now let's get into some specific terminology with a tree. So you have your root node, as I explained before, and then you have some sort of parent, and then it's child nodes. So root is just the starting node that begins the tree, and then sibling nodes share the same parent. So as you can see, they're siblings. And then an interior node is a node that is just like inside. It's not the root node, but like it's in between like the very bottom and the very top. So these interior nodes is a node that has one or more children, but it's not the root node. And then a leaf is a node that's at very bottom, and this node does not have any children at all. So this is why we call it leaf, because it's the edge of the tree. So then let's get into some other vocabulary, just describing these nodes as well. So you can have a depth. So the depth is just the number of edges from the root to the node. So as you can see from the diagram, we have a depth of 0. This is the root. And then going from this root to the first depth, this is depth 1, this is depth 2. And then height counts from the top, but height can be any node at all. So like we can have height 0, height 1, 2, and 3. This is a difference. And then we can just see like this total tree will have a height of 3 as we start from counting from 0. And then there's also some types of trees, just to you guys knowing this. So types of trees. So whenever people refer to a binary tree, it means that each node only has at most 2 children. And then a binary search tree is a very specific type of binary tree. It's the type of sorted binary tree where each of the nodes, the left child is smaller than the parent, and then the right child is larger than it. I'll show you a diagram of this to help you guys out. And then we have a balanced tree as well. This is just a general constraint that entails the tree has these type of properties. So the left and right subtrees, the heights differ by at most 1. The left subtree is balanced and the right subtree is balanced. So this type of constraint is actually recursive. As you can see, this is like a base case, and then these are just recursive elements. So you can see some pictures. So here's a binary search tree. As you can see, we start at 7. So the left node, which is going to be 2, it's smaller than 7, and then the right node, 9, is going to be larger than 7. And then as you can see here for the 2, 1 is smaller than 2, and then 5 is larger than 2, and then 9 here, 14 is larger than 9. So this is a type of sorted binary tree. That's very useful. Sorry for the phone in the background. This is very useful for some operations. And then also we have a balanced binary tree. Just generally, as you can see here, the height between like these two only differ by 1. And then this is an unbalanced binary tree, as you can see. This is just nice just to know like the general concept. As you can see, this is generally just balanced, and this is generally very unbalanced. All right, let's get into part 2, graph representation.
Yeah, so that's gonna be me, guys. Graphs are kind of a very complex data structure, and they're not built into most languages, so you need to kind of define it yourself. And I'll be going over 2 methods that you guys can represent them in your code. And the first of which is an adjacency list. And an adjacency list is a collection of unordered lists that will represent a finite graph. So most adjacency lists use a hash table, and in Python that's a dictionary. And if you guys remember from I think 2-3 weeks ago, a hash table is where a key has a key which points to a value. And in specifically for an adjacency list, these specific keys will be nodes, and these nodes will map to a list of connected nodes. And the way I like to think of it is that Each key will be a node which maps to the adjacent or directly connected nodes. And the memory of an adjacency list is very dependent on the number of edges it has in the graph. And the really cool thing about adjacency lists is that you can kind of check if a node is connected to another node in OK time, which means where k is the number of nodes or neighbor nodes. And a neighbor node is going to be different, or the number of neighbor nodes is going to be different for each specific node. Um, it's very fast to go over all of the edges possible in a graph. It's simple to add an edge and delete a node in an adjacency list. I'm going to go over one example so you guys can kind of understand and visualize what an adjacency list is. So over here we have a graph on the right. It has 1, 2, 3, 4, 5, 6 nodes, and it has multiple edges in it. So if you guys see on the left, we have a graph, and in Python this is a simple dictionary. And the key that we have on the first line of the dictionary is A. A is going to map to a list of nodes. And if you look on the right visually, A points or is connected to B, C, and D. And because of that, we basically put all of these nodes into a list. And it's kind of neat in that way, so that if A is connected to B, if you go on the next line, you can see that B is connected to A. And since this is a unweighted, undirected graph, we usually use adjacency lists for those. But it's kind of difficult to represent a weighted and directed graph in an adjacency list. But we'll tell you how to use that later on in the slideshow. If you guys want to see some more just go back. If you guys want to see some more examples, you see B is connected to A, C, E, C is connected to A and B, and so on and so forth. There's not really a way you can specify the direction an edge is going through, or the weight of a specific edge, and that's why we use something called an adjacency matrix. So yeah, go to the next slide now. So an adjacency matrix is a square matrix that represents the finite graph, and this graph can be weighted or directed, or both. And the way it works is that we have all of the nodes mapped on the x-axis ish, and on the y-axis. And if you look on the bottom right, and it's a really good example here, you can kind of see that we have 5 nodes, and these nodes are called A, B, C, D, and E. And the cool part about this is we basically have all of the nodes on the right, or kind of like on a top down view, and all of the nodes from a left to right view. And the values that intersect from each node will either be true or false. If it's true, that means there is a connection between both of these nodes. And if it's false, that means there's no such connection. So you can probably see there's a diagonal. There's usually a diagonal of 0, but if you look at D and D, that means D is connected to D, so it kind of has a loop. So this specific graph, just by looking at its adjacency matrix, you can see that D is connected to D. The cool part of an adjacency matrix is if you want to find if two specific nodes are connected to each other, it'll just take one of time. So let's say if we want to see if B is connected to C, we look on the top right, we see B, and we go down, and then we see C. We kind of cross and we find the intersection, and we see 0. That means false. That means they are not there. The downside of an adjacency matrix is that it takes a lot of memory. Just go back. Yeah, it takes a lot of memory. As you can see, it's an n by n matrix, and let's say we had a really large graph that had multiple hundred nodes. You can kind of see how large or how much memory it will take. And it's really, really slow to iterate over all of the edges. But that's why we have something called an adjacency list, right? So depending on the problem you see, you'll easily be able to find out which type of representation you can use and which one will be most helpful for you. Let's go through some examples.
Alright,
Go to the next slide. Okay, yeah. So here we have a weighted graph, and like I said before, an adjacency list, you can't represent, or it's hard to represent, a weighted graph, and this is where you use an adjacency matrix. So similar to before, we have the nodes on the top, and we have the nodes on the left, and we kind of want to map the intersection representing a true or false. But the difference here is that instead of just showing true or false, we can say if there's a connection, we just write the cost to travel in the indices. So what's the cost to travel from node 1 to node 0? If we just look at the adjacency matrix, it takes 2, and that matches with our graph. And the cool thing about this is we can immediately determine if two nodes are connected, just if it's 0 or not. And before we had a boolean representing it, so it would be 1 or 0. There isn't that much of a difference here, except that 1 turns into a value, and that value is going to be specified by your input or the visual graph. Go to the next slide. So similar to a directed weighted graph, we can also have a directed graph. And a directed graph, like Kevin mentioned, is basically a node pointing to another node. It's a one-way street, or it can be a two-way street, depending on how you look at it, or like what the graph specifies. And the reason why directed graphs are so hard to represent in an adjacency list is because there's no like one certain way we can go from one node to the other. And by convention, in an adjacency matrix, the direction of the arrow from node A to node B will go from the vertical column to the horizontal collection. So if we look at, let's say, the first node 1, and it's pointing to number 2. So on the left, we see that 1 will point to 2.
Here,
And
here.
the reason it points to 2, we can kind of verify that if there's a 1 there, and 1 means true, right? So that means there's a connection. But let's say we didn't know it was vertical to horizontal, or we never specified it when we were trying to solve the problem. We try going from the opposite way. We go from 1 from the top down to 2. There's a 0 there, and you're probably like, okay, why is there a 0? It's because you can't go from 2 to 1. It's a one-way street. And this basically means, and if you look on the left side, you can see that nothing goes to 1, and that's true on the graph. This basically means you want to specify the convention or know the convention that you're going to use before you make the adjacency matrix. And this can be a common error that you guys make. Let's say I want to use vertical to horizontal, but then in your code you go from horizontal to vertical. You got to specify it, and you got to get used to and accustomed to one specific collection convention. Yeah, it's not always go back. Yeah, it's not always going to be symmetrical, and that's because it's directed, and you can see node 4. It basically it's kind of like connecting back to itself. Yeah,
All
it's
right.
just like a pointing back to itself,
All right.
and that's why 4 is connected to 4. Yeah.
All right. I'm also going to
Okay.
interject here. An adjacency list, you can technically show weights and direction, but it's very like iffy. Like I'm just gonna go back to here. Like if you want to show weights, instead of just storing a key in this array, you'd store like pairs for each of these, like B, and then have some sort of number. But that kind of gets very iffy. And then also you can show that A goes direction that A goes to B, but in this B entry you omit this completely. So in this scenario, it would be A points to B and points to C. But if you just remove this, then B would not point to A. So
Yep.
it's possible, but depending on the situation, you want to just look at what's clear. For weights, it's especially very useful to use an adjacency matrix. For direction, you can technically do it for either or, but it's a lot more clear. All right, let's get to part 4. Some graph algorithms.
Yeah. So I'm gonna go over 3 graph algorithms. DFS and BFS. That's gonna be depth first search and breadth first search, and the last one is gonna be special. Okay, so let's go through depth first search first. It's a tree traversal or graph traversal algorithm that goes through each node in a graph depth first. So kind of think of it as it's gonna explore as deep as it can, and then it's gonna come all the way back out. And we can kind of look at the diagram on the right, and we want to pick a starting node, and in our case, it's going to be 1. We look at the connected neighbors to 1, and that's going to be 2 and 3. Since 2 is less than 3, we just want to go to 2 first, just because of like convention. And we look at 2, and then we see that 2 is connected to 4 and 5. And then we explore 4. Once we explore 4, we realize that there's no connected nodes that we haven't visited. And from here, what we do is we backtrack to 2, and then we go to 5. And then once we explore 5, or like record it or do whatever we want, we go back to 2, and we see that there's nothing we can do with 2, so we go all the way back to 1. And then 1 is directly connected to 3. And the important thing to do is whenever you're going through DFS, you want to keep track of your visited nodes. You want to make sure you don't waste time and resources visiting nodes that you've already been on. Yeah, so keep track of like all the visited nodes, and there are three basic steps that you can use in DFS, mainly recursive DFS. You visit a vertex S, you mark it visited, just so you don't visit it again, and then you will have a list of neighbors, or like from your adjacency list or adjacency matrix, you'll know all of the neighbors of that specific node. You want to recursively visit each unvisited vertex. And this is basically going to go into a recursive tree, and each tree will end by itself at one point or another when there are no more nodes to visit. So that's depth first search. The code examples will be going on next week. So this week we're just kind of go over the algorithm.
Yeah, and the
Um,
concept. It will be a lot more clear about how you be able to define this. And summary, what Aditya said, depth first search. You go to the very, it's like depth first, so you go to the very like deepest place that you can go to. That's a good way of remembering it.
yeah, yeah. The second algorithm is breadth first search. And breadth first search is kind of the opposite, or it's very different to depth first search. This time we're trying to go through each node in layers. So in our graph we have, or on the example we have two layers, and a layer is kind of determined by the amount or the height or distance it away, or how far it is from your source node. So the nodes 1, 2, and 3 are all one step away from your source node. So that kind of tells us that it's on layer 1. And then you can kind of see layer 2 is just 2 steps away from your source node. Okay, so the way we kind of do breadth first search is we look at our starting node, and we look at all of the neighbors it's connected to. That's going to be 1, 2, and 3. We put all of them in a queue, and we search through them in that specific order. We explore 1, we explore 2, and then we explore 3. And after we're done that layer, and after we've marked them all visited, the queue will go on to number 2. Go on to number 1. We'll go back to number 1. And then since 1 and that specific layer is going to get connected to 4 and 5, we add 4 and 5 to our queue. And then from 2, it's going to go to 6. And we're going to add 6 to our queue, and then 3 is going to go to 7, and we're going to add 7 to our queue. And in this specific order, we're going to be going through each of the nodes, and once we visit it, we're going to mark it visited. And breadth first search can be used to find the shortest path between two nodes, because if you think about it, the source node is kind of can be like your beginning, or like your starting point of your travel, and the last node that you're trying to find will be your destination. And the amount of layers it is, or how far away it is, will kind of determine or find the shortest path between both of those nodes. Breadth first search, um, these breadth first search and depth first search are two algorithms that are like you should understand, and you should really, really understand them, because you guys already saw the next slide, Dijkstra's. Dijkstra's uses some of breadth first search's knowledge, and in a lot of interview questions and a lot of competitions, these two algorithms are going to be probably the best ones that you can use. And if you understand them, you'll be set. And I highly, highly recommend you do not memorize this. You need to understand them. If you memorize this, that's the worst thing you can do. You want to make sure you understand what's happening in these algorithms.
Yeah. I was gonna add breadth first search and depth first search are your traversals, so this is the way you're gonna be going through it. Like normal arrays that you've seen, like it's a very simple. You can just go from element 0 to the endpoint like iteratively. But breadth first search, depth first search requires these sort of algorithms to know how you want to traverse this. All right.
Okay. We got Dijkstra's. Okay, so Dijkstra's is used to find the shortest path. Hopefully, all of you guys have heard of Dijkstra's. If you haven't, it's very popular. So I'm just gonna go through an example and walk through how Dijkstra's works. So Kevin, you gotta do a lot of clicking.
Yeah.
Okay.
All right.
Okay. So first, yeah, go ahead.
I will say some. It seems like some of you guys aren't even listening to the lesson at all, because some of you are just deafened, which quite saddens me, and are just here for the club credit. Shake my head. All right, let's get back to the
Ah,
lesson.
that's okay. Okay. So here we have a weighted graph, and I'm going to say our big starting point is going to be the top left node, and we want to get all the way to the far right. And we want to, and the number or the units that we're going to use is money. So we want to minimize the amount of money that we want to use to go from the top left node all the way to the right node. And the way we use this in Dijkstra especially is we want to kind of break it into sub problems or tiny, tiny problems. And we want to see how much money it takes to go from one node to another node. So just click. Yeah, so obviously it takes $0 to go from your starting position to your starting position. And we want to mark everything else as infinity because we don't know how much it's going to take. And we can just assume it's going to take the largest or longest time. Now we kind of take what we learned from breadth first search and we look at the directly connected nodes from our source node. We have the bottom one, which it takes 4 to get there, and we have the middle one, like the right middle one, the left middle one. Yeah, that one. And that takes 4 too. So click on it, Kevin. Okay, so yeah, um, we kind of travel from the direct connection, and we see that 0 plus 4 is 4, and 0 plus 4 is 4, and now we know the minimal time it takes to go from, or not the minimal, not yet, the amount of time it takes to go from one node to the other node. And just like BFS, we continue to explore and we keep track of all of our nodes in something called a priority queue. And a priority queue is a queue, except it automatically gets listed if it's kind of like a list. It's sorted. It's a sorted queue. Think of it that way. So we go from our bottom all the way in our bottom left node, and we see that we have one more connection that we can go to. You can click, Kevin. 4 plus 2. So that means we're basically going to go down and then up right. And according to that travel pattern, that's going to take us $6 to get to that specific node. But since the already like occupied value was 4, there is no point of making the value that we travel to 6 because 6 is greater than 4. And obviously, we're trying to save money here, not waste money. So we just don't even think about that path. And in this small subgraph, we kind of realize that the fastest path to that middle node is just a direct connection. From here, we kind of do what we did before, and we go through all of the direct connections from the middle node. And we see the top node. Can you click, Kevin? From the top node, it goes 4 plus 3, which is $7 to get to that node. Directly in the middle, right to our destination, it takes 4 plus 6, which is $10. And at the bottom, it takes us 4 plus 1, which is $5. And now that we've kind of gotten into the near or the end of the algorithm, you can kind of see that we already have a solution. We can see, it takes $10 to get to the end position. But the thing is, once we get a value, we can't. There's always going to be a better value, or we have to make sure it's the best value. We don't know if it's the best value yet. For now, we can record it as $10 because it takes 4 plus 6. But now we should go through the two other nodes or the two different paths. So we can go from the bottom, and we can see that 5 plus 3 is 8. Can you click? And 5 plus 3 is 8, and 8 is less than 10. That means we're saving money here. And since 8 is better than 10, we replace that 10 value with 8. And this basically means we've gotten a better solution, but we're not done yet. We haven't explored all of the nodes or all of the paths. And finally, we go to the top one, and the top one's going to become 7 plus 2, which is 9. If you click. And since 9 is greater than 8, there's no point of changing our final value. And once our priority queue is done, or it's empty, and we visited all possible paths, we just look at the value that we associated with our destination, and that's going to be the shortest path or the shortest cost to go to that specific from our starting point to our ending point. That's basically how Dijkstra's works. This is a really scuffed explanation. You could probably find better explanations like on YouTube or something, but yeah, that's Dijkstra's.
Yeah,
Um,
it was just
Really
something.
good, really good explanation, Aditya. I just want to mention everybody that attendance is open, so make sure to do that.
All right, all right. We'll be wrapping this up, I guess. Okay,
Yeah,
and
well,
we just wanted to show you that Dijkstra because it's something that's a really cool application. It's also something that one of my friends, I won't mention his name, he's I think he remembered all this, very infatuated with this algorithm, but let's continue. Alright, and then here's some applications as well. Aditya?
yeah. So this is basically wrapping up what Dijkstra's is. If you guys take grade 11 and grade 12 CS, Chapman talks about it a bit. I don't know about grade 12, but in grade 10 he just like introduced it to us, and it was kind of cool. There are a lot of large scale applications of Dijkstra's, like social networking applications, telephone networks, and finding locations on a geographical map. So like Google Maps, yeah, it uses Dijkstra's to find the shortest path from one place to another. Obviously, Dijkstra's is not the only algorithm that you can use to find the shortest path. There's also something called A-star search. I'm not sure if we're going to go over it next week, um, but keep in mind that there are other solutions to problems, and yeah, just remember that.
Alright, and
That's all I
then
have to say.
this is just wrapping everything up. Okay, so just the topics of a graph. Graphs are a very big study of computer science in general. There's so many topics, but we've basically given you guys the basics, the tools that you really need. And then here are some topics. So first we went through the basic traversal, just traversing through a graph, DFS and BFS. If you wanted to know about the shortest path, we have different types of algorithms for different types of graphs, so if it's weighted or if it's directed or not. So we have Dijkstra's, we have Bellman-Ford, Floyd-Warshall. I'm just listing these out just to let you guys know that there's a lot of things. We also have spanning trees as well. Minimum spanning tree is basically just saying, okay, so in this graph, what's like the minimum amount of edges we need in order to be able to be connected to like all of these nodes, and that's useful for some of the CCC questions. I actually ran into a couple, and then some of these algorithms that you would use is Kruskal and Prim, and they involve like a union data structure, and then some other graph topics as well. Just to let you know, like the depth that this is at is that there's backtracking types of questions. There's questions about connectivity. So if 2 points are connected, they might ask you that. There's paths and circuits, and there's flows and cuts. Paths and circuits, flows and cuts, similar to like applications with real world things like actual like circuits. And flows and cuts would model maybe like if each node like is a container that contains amount of water, then like how much like with this amount of water, if you put it into like this sewage kind of system, would it be able to like hold everything? And then it also gets into some other properties. But that's some other graph topics. That's the end of our presentation. Hope you guys enjoyed this week's lesson. This week's lesson was a lot of topics, a lot of theory. But hopefully next week we'll be getting into at least like some of the code examples, because code examples are very important for you to know in this topic. Next week we'll definitely be covering DFS, BFS, and then other things as well. We might look into some other fun algorithms for you guys. All right, but that's about it.